Well, I don't think you can deny that that was pretty exciting. The electrolysis of water. So, not surprising, this video is going to deal with this process of electrolysis. And so, electrolysis is, in essence, the opposite of the galvanic cell. So, we utilize electricity. So we add electricity, we harness electricity, and we can then generate or cause a non-spontaneous reaction to occur. So that's the opposite of a galvanic cell. So in a galvanic cell, the electrochemical process spontaneously generates potential, but we reverse this, and we reverse it by adding electrical energy. So maybe not as exciting as electrolysis of water. You've seen this in action all the time, and this is with rechargeable batteries. So be it a simple battery you can put in a flashlight or a handheld device or whatever, or a car battery. We essentially, the batteries are in one hand a galvanic cell by providing that electrical energy to power your device or your car. But on the other hand, if we reverse that reaction, if we add a current by plugging in the batteries into the wall and the recharger where the batteries go, or using the alternator in the motion of the wheels, we recharge a battery. We reverse that spontaneous process, and we essentially, one can look at it as we kind of rebuild the battery. So here's a simplified electrolytic cell, and we talk about the electrolytic cell as a molten ionic compound, or it could be aqueous. So that's a solution containing ions. But let's talk about it in the ionic stage first, and we then know these as electrolytes. Electrolyte can allow the movement of charge, and so electrolysis occurs if you have an electrolyte and if you have these charged poles, just like we have in a galvanic cell. Okay, so this is known as electrolytic cell and electrolysis cell. So a couple of differences from electrolytic and galvanic. So again, electrolytic, there's my anode, positive charge. That's a big difference. Here's my cathode, negative charge. That's a big difference. And the main difference then is the fact that you have electrolytes, which we have in our galvanic cell, but we have electrolytes in a single chamber here in an electrolytic cell. And the reason for that is the charge of the electrode. So this positively charged anode can attract the anions. Negatively charged species is attracted to the positively charged anode. So it's still anions to the anode, but the charge is different. But negative attracted by positive. And so therefore at the cathode, we still attract cations, but the cathode is negatively charged. So this positive species will migrate to the cathode. In terms of other things in this reaction, what's going to occur at the cathode here with our molten sodium chloride, or liquid sodium chloride, we have Na plus electrons moving to the cathode. And so what type of process is that? Plus and a cation plus electrons yielding something neutral, that is still a reduction. So reduction still occurs at the cathode. If you look at the other side of things, we have our anode and we have chloride ion yielding chlorine gas and 2 electrons. So that is my oxidation. So we still have oxidation at the anode. So in many ways, the cells work the same way. Just make sure you realize this is a big difference. This is the major difference. The charge of the electrodes, the anode and the cathode, is reversed in an electrolytic cell. All right, so if we want to look at the overall equation for this electrolytic cell, and we want to determine the voltage required. Remember, now we're going to apply a voltage. So we're going to apply this voltage. Well, how do we go about determining that? Well, it's pretty much the same as we would do in a galvanic cell. So here is a half reaction at the anode. Remember, oxidation occurs at the anode. At my anode, I'm oxidizing chloride ions, so I produce chlorine gas and 2 electrons. And from my table of reduction potentials, there is the cell potential. Now I've reversed this equation, so I've reversed that one. You might recall chlorine is quite a strong oxidizing agent, so it would be reduced typically. That is going to be a positive value in a standard reduction potential table. But because it's now being oxidized, it's the reverse. It's a negative E0 cell. So there's my anode. At my cathode, I have the reduction of sodium ions. So sodium ion plus electrons yields sodium liquid. Remember, this is molten sodium chloride. And so there are my two half reactions, an oxidation at the anode, a reduction at the cathode. Don't forget, I need to balance this. I have to balance the electron transfer before I go any further, so that's going to be 2s. Now I can bring it all together, and I have the electrons being basically cancel out, they're like terms, and so I get 2 chloride ions plus 2 sodium ions, yielding chlorine gas and 2 sodium atoms, liquid. And my E0 for the cell, again, it's just the addition of those two, and so here I'm going to have 9, 6, and that's 4, so negative 4.09 volts. So a negative value. Now, that negative value is different from a voltaic cell, but it should make sense. That is the current I need to apply. I have to apply 4.069 volts. It's negative, meaning a current is required. Positive, spontaneous generation of electrical potential. Negative, electrical potential is required. So again, hopefully you see the process of determining the overall equation and the E0 for the electrolytic cell is really not that different. On a large scale, we can electrolyze molten sodium chloride, and we do this in something called a Downs cell. And so here's a bit of an outline of how a Downs cell works. First of all, it takes place at high temperature. Molten, this is liquid. It actually takes place at about 600 degrees C with calcium chloride. Now, I'm not going to go to the details of why that is, but that's what we're doing. About 600 degrees C, NaCl mixed with calcium chloride. So this is all liquid, and so here's your graphite anode. So that's an inert electrode, and the anode, what happens at the anode? Well, that's oxidation. So there's the oxidation half reaction for chloride ion. So chloride ion yields chlorine gas, and so chlorine gas bubbles up. It's a gas, it's less dense than the molten solution, so it just goes up and it raises up. Here, the actual cathode is this, all this steel, it's called, or iron, and sometimes it's iron. And so there's the reduction at the cathode. And so again, the reduction process takes sodium ions and yields liquid sodium. Now, liquid sodium is actually less dense than sodium chloride as well. So the liquid sodium actually rises, and it just gets piped off here. So there's liquid sodium, that little gray layer, and that's how you collect your sodium. So this process with, if you just to remind you, your positively charged anode, remember opposite charge with your anode, and your negatively charged cathode produces a lot of chlorine gas and a lot of solid or liquid sodium, which can then be cooled down and solidified if need be. So anyways, quite a common process done on a large scale. Now, just to finish off then, you want to be aware of the differences, and as you'll see, there are not too many differences. So here we're talking about a Downs cell, so that's a voltaic cell. So voltaic cell, spontaneous. So this is based on differing reactivities of metals or ions, and you get that from your table of standard reduction potentials. A voltaic cell converts chemical potential energy to electrical energy. So that's a spontaneous generation of electrical current. So it does that via a chemical reaction. The anode has a relative charge that is negative, and the cathode has a relative charge that is positive. And those are those designated charges. So what happens at the anode? Well, here's another memory aid for you if you want. An-ox. So at the anode, you have oxidation. Well, by extension, then what happens at the cathode? Well, reduction occurs at the cathode. So those are two memory aids you might want to use. The conduction of this charge is said to be electrical, and that is it's conducted through a wire. So it's electrical conduction through a conducting wire. So that's, in a nutshell, what happens in a voltaic cell. Well, how about the electrolytic cell? So here's our electrolytic cell, and that would be, for example, a down cell. So it is non-spontaneous. So it requires electricity. That said, it's still based on the differing reactivities of metals and ions, and you still have to go to your standard reduction potential table. In an electrolytic cell, we take electrical potential energy, we convert it to chemical potential energy. So we're doing the reverse process here. The electrical current provides the energy required to reverse a spontaneous reaction. In terms of the anode cathode, the anode has a relative charge that is positive. So that is something you want to make sure you realize the difference. This is really the main difference. So the anode is now positive, the cathode is negative. What happens at the anode? Well, it's still oxidation and it's still reduction at the cathode. So again, that hasn't changed. The conduction is said to be electrolytic conduction, and that's what I was talking about before. This is through a liquid or a solution. So this is why an electrolytic cell does not require separate containers, so to speak. You don't have to separate the two half reactions because the conduction is via the ions that are either in solution or in the molten state. So there you have it, electrolytic cell. Not a great deal different from voltaic cell in terms of how they operate, but quite a different process in terms of what happens. Spontaneous reaction for voltaic, non-spontaneous reaction for electrolytic. And that concludes this video.